All right, so here's number 19. Using the modified form of Kepler's third law, calculate the orbital period in days of Gliese um, 851d, which is an exoplanet. It has a mass of uh, 7.1 times the mass of the Earth. This would be considered a super Earth. Um, anyhow, uh, so that part doesn't matter at all. What the mass of the planet is, that's just adds a little extra information. The star Gliese 851 is a red dwarf star and has a mass of so this is what we really need is the mass is 0.31 times the mass of the sun. Solar masses are masses of the sun. So the mass of this star, right? So let's write that down. The mass of this star is 0. It's it's 31% the mass of the sun. So it turns out that the mass of our sun is 2 times 10 to the 30th. Right. So if I multiply this times 2 times 10 to the 30th kilograms. All right, so that'll be the mass of this star, which we're going to use in the modified version of Kepler's third law, where it's solved for the period. So we're going to that's the m that we're going to use right there. It has to be in kilograms. All right, so let's calculate that right now. All right, so that's pretty trivial. It's just 0.31 times the mass of our sun, which is 2 times 10 to the 30th. All right, so there it is. Oh man, I really hate this calculator. So let's see. So this is going to be. All right. Anyhow, 1, 2, 3. All right. So let's see. So there's 6. There's 12. There's 18. It's hard to count in 6 by 6s. There's 24. There's 20. I already lost count. Hold on, let me do it again. All right, so it turns out it's 6.2 times 10 to the 29th. All right, so now I've stored that in the calculator. All right, so that's right there. Just to prove to you that this is 10 to the 29th, I'm going to take that number and divide it by 1 times 10 to the 29th, and that'll give me 6. This should give me 6.2, and of course it does. All right, so that's that. The mass of this is 6.2 times 10 to the 29th. All right, and then let's see. So what's the next thing we have to do? They give us the semi-major axis of this. All right, so the semi-major axis is the average distance that it travels away, and so that the exoplanet travels away from its star. And really, in this equation, that's what d is. But d has to be in meters. All right, so D is all right. So let's do this. So D is where is it? Oh, there it is. 0.22, 0.22 astronomical units, and so it turns out that in 1 astronomical unit, right, if I wanted to go directly to meters, it turns out it's 1.5. Let's see, what is it? 1.5 times 10 to the, I think it's 11th. Hold on. All right, so yeah, I verified that. All right, so it's 1 astronomical unit, which is 150 million kilometers, turns out to be 1.5 times 10 to the 11th meters. All right, so if and I think that's on the formula sheet. If you multiply that times 0.22 AU, so here we go. So times 0.22, that'll be the size. That's what D is in meters. All right, so let's see. This is 1, 2, 3. There's 6. There's 9. So it's 3.3 times 10 to the 10 to the 10th, 3.3 E10 meters. All right, so now we're ready to go. So now I have everything in the proper units. This is in kilograms. This is in meters. All right, so I've got those two numbers. All right, so now I'm going to plug everything in. So it's going to be the square root of 4 pi squared, all right, times d, which is, the case, what I just calculated, 3.3 times 10 to the 10th cubed divided by big G, which is 6.67 times 10 to the minus 11th, but also divided by the mass of this of the star. Remember, the period it's the period of the planet, but the planet is orbiting the star. So the star's mass is 6.2 times 10 to the 29th, right, and that's in kilograms. All right, so this will give us the period in seconds. All right, and we'll convert that to whatever they want it. I guess days. All right, so we'll convert that in just a moment. Let's get the numerical value. All right, so let's see. What was this? This is the oh yeah, that's D. All right, so I got to cube that, raised to the third. All right, and then times 4 times pi squared. All right, and then divided by 6.67 times 10 to the minus 11th equals, all right, and then all I've done is this part of the calculation, and now I have to divide it by the mass of this sun, of this particular star. All right, so that number's right there. So what I just circled, and then divided by 6.2 times 10 to the 29th. All right, equals. Now remember, that's still under the square root. So I've got to take the square root of that. So there it is. All right, so that's the period in seconds. So 5.86, I don't know, something like that. 5.86 times 10 to the 6th seconds. All right, we're not gonna round that right there. We're gonna keep that in our calculator, and then we're going. So do you see, there it is? 1, 2, 3, 1, 2, 3. All right. So we're gonna take that number again, the unrounded version of it, 5.86. I rounded it just for convenience, times 10 to the 6th seconds, and then we say, all right, well, there are, of course, 60 seconds in 1 minute. All right, and then there are 60 minutes in 1 hour, and there are 24 hours in 1 day. And I think that's what they want. They want to know what it is in days. All right, so we're going to take this number, this number that's in our calculator already, and we're going to divide it by 60. Where's my calculator? Come on. There it is. Spend more time looking for the calculator. All right, so that's the number, and then I'm going to divide it by 60 squared, because it's 60 times 60. All right, equals, and then divide that by 24. All right, so this will give me the number of days. All right, so I'm going to round that to, what does it say? 1 place past the decimal. So it's going to be 67.79. So it's going to be 67.8. So the answer to number 19 would be 67. So in days, this would be 67.8 days. All right, so that's how long it takes this exoplanet to orbit Gliese 851d. No, I'm sorry, that's the name of the exoplanet. Gliese 851 is the star. So anyhow, that's all right. So here's number 20. The basic idea here is that all we have to do is take the ratio of the area of the Earth to the area of the Sun. All right, so that's part A, and then part B, it's the same thing, but it's not. It's the area of Jupiter to the area of the Sun. All right, so here's part B, area of Jupiter to the area of the Sun. All right, and just as a quick reminder, the area of anything that's circular is just pi r squared. All right, so pi times the radius of the Earth squared divided by pi times the radius of the Sun squared. And you just have to make, of course, the pi's cancel, so you don't have to really worry about that. All right, so let me quickly do this one. They give us the rate. They give us the radius of the Earth and the radius of the Sun for part A. Let's quickly do that one. All right, so the radius of the Earth is what is it? 6,378. We normally just say 6,400, but anyhow, to be more precise. All right, and then we divide that by the radius of the Sun, which is 6.96 times 10 to the fifth. All right, and remember it's the ratio squared, right? So it's the I could either square both of these or just take the ratio of the Earth to the ratio of the Sun, which I just did, and then square that ratio. All right, so that works too. And so all I have to do is square this. All right, so squared, and that seems like, all right. So we're not quite at the answer. It says to represent it as a percentage. So to represent this as a percentage, I've got to multiply this times 100, right? Times 100, and that will get me. In terms of percentage, when the Earth is right across the Sun, it blocks 0.0084. It's 00839. So 0.0084% of the Sun's light. All right, and let's do that for Jupiter real quickly, and we'll get something, a bigger number. All right, so Jupiter is 71192 divided by 6.96 times 10 to the fifth equals, and then of course again you got to multiply by 100 times 100 to put it on a percentage. All right, so I think I did something wrong. Okay, that's better. So when I just didn't type the numbers in correctly. So when I did the ratio of the radius of the Sun squared divided by the radius of Jupiter squared divided by the radius of the Sun squared, this is the number that I get. And then if I multiply that times 100, that'll put it in as a percentage. So there it is. So 1.0, if you will, 0.46 or 1.05. All right. Let's go back to this. This turns out to be, when you do it as a percentage, 1.05%. All right. So when Jupiter blocks the sunlight, it's blocking a little more than 1% of the light. All right. That is the last problem.